Oh, okie dokie, here we go. What we're going to do here is we're going to talk about confidence intervals for a difference in means. And we're going to do talk about a plan for a two-sample t-interval for the difference in mean 1 minus mean 2. All right. And so the first thing is we're going to go through the four-step process. As you can see here, we're going to state the parameter and level of significance. We're going to plan, in this case, a two-sample t-interval for the difference in means. And then we need to test conditions. And the conditions are, yes, it needs to be random, it needs to be a 10% for independence, and we have to have normal. Normal, like in all the other ones, when you talk about means, population is normal. Either you're going to use a central limit theorem, where you have a sample size greater than or equal to 30, or if you don't have any of these, you're going to graph out the two sample distributions and then see if there's no strong skews or outliers. From then, we can go into the do, and the do we see right here is that we're going to find our statistic, our statistic right here, and then we're going to add a plus our critical value. Our point of estimation, point estimate is right there. Critical value is right here, and then our sampling. All right, our standard error is located here. Notice how we take our variances. Now, one thing when you're finding your critical value, make sure your degrees of freedom. We're going to use the smallest value for n. All right, of these two, so we're going to compare the two. So the smallest of the two sample sizes, we're going to use that and subtract 1. So we're going to be very conservative to make sure that we have a large enough interval where we are sure that we will have the true difference in the means. Okay, true population. All right, so with that, let's try a problem right here, my friends. Okay, and this is an example of one where a class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rate. 20 students in the class volunteered to take part in this experiment. All of the students measured their initial pulse rates and beats per minute, and then the teacher randomly assigned the students into two groups of 10. Each student in the groups drank 12 ounces of cola with caffeine. Each student in the second group drank 12 ounces of caffeine-free cola, and then they measured their pulse rates. Here is the difference from the beginning to the end, caffeine and no caffeine. From here, we're going to construct a 95% confidence interval for the difference in true mean change in pulse rate for subjects. We have that. Okay, so what do we have here? Well, the first thing is we're going to do is we're going to write out our parameter. Okay, we're going to take out our parameter here. And with our parameter, all right, our parameter is going to be mean 1 minus mean 2. Mean 1 minus mean 2. And what is this? Well, this is the true difference in the change, difference in the change of the mean pulse rates, where it's going to be caffeine versus no caffeine. All right, and that's what we have there. And make sure I spell it right. Okay, there we go. And from here, and that is our parameter. Now, we're going to talk about a significance level. And since we want a 95% confidence interval, all right, we're going to then take this and we're going to just state a, all right, 95% confidence, all right, and 95% confidence level. Okay, so that's what we got there. All right, so with that, my friends, let's continue on. So that's our parameter, that's our state. So now the next thing is we're going to perform a, all right, one, or it's actually two, sample, all right, t interval for the difference in means, okay? In means, okay? And that's going to be mean 1 minus mean 2. Now, we're going to test our conditions here, all right? And this difference in means, as we know, is going to be mean 1 minus mean 2. And so what we have right here, right now, is that we want to first say, do we have a random? Okay, so in this one right here, all students measure pulse rates, 20 students volunteer to take part in the experiment, all students measure the pulse rate, then they get randomly assigned. So yes, random assignment. Okay, random assignment. Now this is possibly an experiment, so we may not have this, but we're going to just say, that we had 20, all right, 20 in our experiment. Is that less than what we have right there of all of them? And we say that for 10% of all of them. However, this is an experiment, as I said before, and so when we have an experiment with a random assignment, independence is all right, we don't need to test for independence because there is random assignment. So whenever you experiment with random assignment, you don't have to test for independence. So next we just have to test if it's normal. Now, unfortunately, our two n values, n1 is 10, and also n2 is 10. We don't know if if the population is normal, and these are definitely not greater than 30. So what we're going to do is we're just going to quickly graph these just to see if there's any outliers or whatnot. All right, and so if we go right here, we have 0, and we go 1, 2, or -1, -2, -3, all right, -4, all right, -5. We go 1, 2, 3, 4, 5. All right, 6, 7, 8. All right, 9 and 10. Okay, and then we're going to just graph the first one. So this is going to be caffeine. And this is what you would do, all right, if you have this. So we're going to graph this, and we have, all right, 5, 6, 7, 8. We have one there. We'll have one there. We'll have one there. We'll have one there. And you can just hear me say you have one there and have one there. All right, and we have 6. And we go there, and we got one there. All right, and we have 4. All right, there, and we have one at 0. All right, there doesn't appear to be any strong outliers, maybe a little bit of skew, but not too bad. All right, and we could do that. Then for the next one, we do the same thing. 0 right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 1, 2, 3, 4, 5. All right, and that's -1 and -5 right there. Okay, so for this one, we're going to do the same thing. We got a 3, we got a -2, we got a 4. All right, we got a -1, and we got a 5. We got a 5, we got a 1. All right, we got a 2, and we have a -1. Definitely not seeing anything suspicious here. This one, no strong skews or outliers. So no strong skews or outliers. So we're going to just say this is approximately normal. Okay, so we can continue on our thing. So approximately normal. All right, so that's how we go about doing that. Now, from here, we're going to then go to the do phase, okay, the do phase of this. And now to do the do phase, what we're going to need to figure out is what is our mean of each one of these. And now we know our mean of this one. We're going to say this is equal to there. We're going to say this one is our second one, okay, right there. And so we're going to find out our statistic, okay? Oops. Don't do it that way. All right. Right there. There we go. Now that's our statistic. All right, we got our statistic right here. And so we're going to take that mean 1 times 2. So we're going to take 3.2 minus 2. Okay, and we can realize that that's going to equal 1.2. All right, 1.2 right there. Now we're going to add and subtract that to our critical value, which is our t value. Now, our degrees of freedom in this case is, since we have 10 and they're both equal, so we're going to say 10 minus 1, which equals 9. So we're going to have a degree of freedom of 9. All right, and when we're doing this, so we can go to our calculator and we can punch this in here and we can say, okay, we're looking for, go to second vars, you can go down to 4, and then we want to figure out an area, which is 0.025. That's going to be where we have 95% confident, and our degree of freedom is going to be 9. Okay, so make sure that's all there. We're going to have paste it, and we're going to go boom. All right, press enter. And it's going, and we have -2.26, -2.26. So we have a critical value of -2.26. And now we want to figure out our next values. Now, from here, you want to also go to your calculator, and you want to enter all these statistics into your calculator. All right, into list 1 and list 2. Okay, so that's what I did right here, list 1 and list 2. Now, if you do this, you can actually go, if you go to stat, all right, and you go to edit, and that's what I did right here. Now I went to list 1 and list 2, all right? And then from here, I go to my stat again, I can go to test. Now with this test right here, if you go down, you can see you can do a 2, all right, sample t interval, okay, which is 0 right there. I'm just going to press 0. All right, now when we have this, we're going to take and we have data. Now it's going to use list 1, list 2. We're going to have this frequency. We're going to say pooled. We're going to go to no, not pooled, even though we probably could do pooled because we do have the same number. It wouldn't really matter. All right, but we're going to just say calculate. Now, this is what you'll notice right here. Our degrees of freedom, the calculation, they do it differently than ours. So they're going to have a different standard deviation than us. However, it does help us out because it does give us all our standard deviations that we need. And so I'm going to just take this and we can maybe compare the two different values when we have that. Okay? And so when we're doing our do, okay, I'm going to take this and I'm just going to write this out so we can have this. And that's what I would recommend for you guys when you're going through and doing this. All right, take and go into sample, to sample t interval. The degrees of freedom might be a little off because our degree of freedom we see are going to be 9. Okay, so that's going to be, it's going to be a different interval. But what we have right here is we can see that we have our means and now we have our standard deviations. So we're going to take this 2.7, we're going to square that divided by 10. And we're going to take this, all right, 2.6, and we'll just go 2 squared divided by 10 as well. All right, once we have that, all right, we can take this right here, and we can go to our calculators again, and all right, we're going to enter that in, and I'm just going to take this out, and we can clear this, and I'm just going to take the square root, okay, and you can maybe fast forward this if you wish. All right, just follow me. Maybe have a double time, and we're going to divide that by 10, and then we're going to add that to 2.62, and we're going to square that, and we're going to divide that by 10 as well, and we have this as our answer right there, and we have a 1. Oopsies. All right, 1.19, 1.19. 1.19. So this is our standard error, just so everyone knows, that's our standard error. So let's find our, all right, margin of error for this particular interval. And so we'll take our calculator again, and we're going to take this and multiply it by, all right, negative 2.26. All right, I guess the critical value could just be positive because it doesn't matter. All right, and what we have right here is going to be, that total is going to be 2.69. 2.69. All right, so we'll go 2.69, 2.69. All right, and then we're going to add and subtract that to 1.2. 1.2. So that's going to lead us into our interval that we want. And so if we add that there, we're going to have our top end is going to be 3.89, 3.89. And our bottom end, okay, if we subtract that from there, is going to be 1.49. All right, 1.49. And you can see from this right here, okay, is that we have these two different values. All right, and it is a little bit different than what we have here. Okay, a little bit different than what we have here. Okay, and when we have this, okay, when we have this, one of the things that you, oh, that can't be right. That can't be right. Hang on, let's do that again. Times 2 point, is that right? All right, 1.19 times 2.26. All right, 2.69, yeah, 2.69, all right. All right, so we have that, I apologize. All right, we have this right here. And now this seems a little bit off, okay? It seems a little bit off when we're having that. Okay, and why is that going to be? That's because I did not subtract it correctly. All right, so when you're going over here and you have this, because you make sure you do it right, you go 1.2 minus 2.69, and I think it's just going to be positive. So you probably already figured this out as I was going through my own little negative 1.49. That should be negative 1.49. Okay, so now when we see this, and we can see that, yes, This is a little bit wider than this one because obviously we had a degrees of freedom that was much smaller than the degrees of freedom that they used here. Okay, and so here is our interval. And so now the question is, what do we conclude? Well, we are 95% confident. Maybe I can take this out. We are 95% confident that the true difference in the mean, what is it here up here? And the mean difference in the mean change of pulse rate, the mean change of pulse rate between caffeine and no caffeine. Fix that real quick. Whoop. All right. All right. Is between negative 1.49 and 3.89. Boom. And that's what we know. All right. So we are 95%. The true difference in the mean change of pulse rate is between these two different values. And that's what we have for our conclusion. So I hope this makes sense. I apologize for all of the little messes up and uncertainty of going through here, but hopefully it goes through the 4-step process again. Find the parameter. Make sure you state what you're planning. All right. Check your things. Remember, if it's an experiment with a random assignment, we don't need independence. If you can't use a central limit theorem, or you don't know the population, if it's normal or not, you have to graph it out just to identify if it doesn't have any strong skews or outliers, which generally it doesn't. And then you go through and do this. You can use your calculator to sample t interval. Check out the degrees of freedom because it generally will be different than what we have here, but it will help you find out your standard deviation and your two different means for each one. Use that to calculate your values. You can use inverse t to figure out what your critical value is here. Multiply them together. Make sure you add and subtract because I didn't do that correctly the first time. Should get a reasonable answer that's pretty close to this. And then you can conclude by stating we are 95% confident, or whatever the confidence level is, that the true difference in the mean change of the pulse rate caffeine to no caffeine is between those two different values. All right. Well, thanks for your time, and I hope this helps you out. Good luck and God bless in the rest of your problems.